Have you ever seen this picture floating around the internet? Have you ever wondered what the heck it was and how it was obtained? Well, you're in luck. Today, we will dive headfirst into these plots. Welcome everyone. I am a science nerd covering the joys of quantum mechanics, and in today's video, we will discuss how to construct the spatial wave function for hydrogen, with, of course, a bonus at the end. By the end of this video, you will be able to identify the hydrogen wave function, this big clunker here, normalize the radial wave function, use that to construct the spatial wave function, and then of course plot and interpret the graphs of the hydrogen wave function. So all of these beautiful looking things here. Alright, let's see what we're actually tasked with doing. In this problem, we want to normalize the particular state R of 2, 0, which is given below. This is also known as the radial wave function, which we'll dive into. And then we want to construct the total spatial wave function here, which is lowercase psi of this particular state. And then of course we want to do that for a couple more states just to make sure that we know what's going on. Before we begin though, I would like to mention that there's a free companion PDF that you can use to follow along. The link is below. Alright, so let's talk a little bit about setup first. We know that from Chapter 2 and mainly Chapter 1 that we discussed the need for normalization. Now that we're going into 3 dimensions, that still has to be true, meaning that the normalization condition extends to the 3 dimensions, and instead of a single integral, we have a volume integral indicated here. And we also know that this has to be true for the total wave function. Noticing that we've been keeping up with separation of variables, this is representative of capital psi in Lm of r, theta, phi, and t. Okay, so we have all parts together here, the radial, the angular, and the time dependent. And we notice that in the magnitude squared, that time dependent goes bye-bye due to the complex nature of the exponential. And we're left with this setup here. So now what we realize is that in order for the normalization to work, we have to settle this through the spherical coordinates, which changes this dv term into the r squared sine theta dr d phi d theta. It's not just a box like we had before. You go back to multivariable calculus where I can rederive that for you with the Jacobian if you'd like. Nonetheless, it's different now. And so what we have to do is split this up into a radial part and an angular part, where we have an r squared coming from dv over our bounded region from 0 to infinity. And then our angular part has to go with a sine theta over 0 to pi for theta and 0 to 2 pi for phi. So everything is starting to come together now from things we've learned in multivariable. And all we are tasked with doing in this particular question is using this radial part here and using that to normalize the given states. So let's go ahead and check that out. So then, here in part A, what we realize is that we were given r of 2, 0, and this means that n equals 2 and L equals 0, as the color coordination suggests. Understanding these forms and being able to identify what they are is half the battle sometimes in many of the physics classes, but especially in quantum mechanics. So I like color coordinating for that fact. But now, as we saw previously, we need to use the radial part of that normalization factor, or normalization setup, to now solve for what we know as C naught, which was given in the initial function statement. Here, though, let's recall that in our last question, we used the recursion relation to find what these polynomials were attached to the exponential, and we noticed that they all led to a term of C naught. The goal of the normalization now is to find out what this C naught is, such that this integral statement is true. So that is the goal here, and now we can just algebra our way through, noting here that the radial part is all real. So we can just square everything, as we see here. And so squaring, what we realize is that this leads to another polynomial, which we see in the parentheses here. And from that, we can distribute the r squared here from there, and the exponential, which reduced by a factor of 2 thanks to the square. And when we do this, what we see is that we're in a perfect situation to set up for the tables in the book. Let's see how that is applied. So when we distribute and split everything up due to linearity of integrals and all that other fancy stuff, what we see here is that we have some degree of r times an exponential with the negative r in it, and of course over dr. Here we have a r of 2, of r of 3, and an r of 4. And in the integral tables, which again is highlighted in the PDF in a little more detail, we set up the whole chart for you. But nonetheless, what we realize here is that the n of 2 for 1, n equals 3 for 2, and n equals 4 for 3. These lead to the expansions here. You could go ahead and integrate by parts and all the other fancy stuff, but that is not the point of what we're trying to do. The author gives us tables in the book, so utilize them to save you time and just form match like we've seen in several other instances. It just doesn't make sense to use your time on that when you're trying to understand the physics. So note that your tools are available for that, and now we can simplify down. The result of the